All right, so this video is going to be on radical additions to double bonds. And so it's basically going to be HBr adding to a double bond, but also polymer chemistry because it's similar. Okay, so here is an example of just HBr addition to an alkene. And under normal circumstances that we're familiar with, right? We form that carbocation intermediate at the tertiary position because it's more stable, and we get our tertiary alkyl bromide. But if we have radical conditions, we get a little bit of a different outcome. Okay, something we, I don't know, might not expect at first, but after we do the mechanism, it'll make sense. Okay, so for radical conditions, we need a peroxide and light, or just peroxide and heat. Okay, and what we end up getting is this guy, this alkyl bromide, which is anti-Markovnikov, right? That bromine adds to the less substituted carbon, and that's not necessarily expected only when we're doing the ionic intermediates. Okay, so if we're doing a radical mechanism, then it's a little bit different. Before we added the hydrogen first and then the bromine, and the radical mechanism we add the bromine first and then the hydrogen. Okay, so this is why we have a different outcome. Light splits up that peroxide. In case you didn't know, that's why hydrogen peroxide is in a brown bottle, so that it's not kind of decomposing in the presence of light. Sometimes it's in an opaque bottle as well, but same idea. All right, so that RO radical removes a hydrogen atom from HBr, which forms a bromine radical. Okay, so this is our initiation step. Right, we have like a sigma bond or two of them, and then we break up some stuff and we get a radical. And then we use that radical, right? So we're going to use that bromine radical for the start of our propagation step. And let's say it reacts with the alkene. Okay, so when it reacts with the alkene, I drew that arrow in the center intentionally. We can go two different routes. We can have a radical here, or we can have a radical here. Okay, which one is more stable? What's going to be the outcome? Well, this is a tertiary radical, and this is as a result of a primary radical, right? Well, we do know that tertiary radicals are more stable, and so cross that bad boy out. Okay, so that's not the route we want to go. So there's our red arrow indicating where the radical goes to the tertiary position. Boom, we already explained why bromine is at the anti-Markovnikov position, the less substituted carbon. Okay, now we can add our hydrogen atom to finish off the mechanism to give us our alkyl bromide as well as a Br dot to go ahead and cycle through that propagation step as again. Okay, now termination. What is the termination step? Well, remember you bring two radicals together and then bada bing bada boom, they're done. Okay, so bromine radical comes together with itself or with another one from bromine, elemental bromine. Done. All right, so a couple notes I want to make. The ionic mechanism, we are going to add Markovnikov, and so that means that the bromine is going to add to the more substituted carbon. Okay, and the radical mechanism adds anti-Markovnikov. Okay, and the way we're going to identify a radical mechanism is by the presence of ROOR, some peroxide, and or light, some radical initiator, right? And then only HBr works, not HCl or HI, okay? Or HF for that matter. HF always sucks though. So HCl and HI don't work. Sorry, I was going to kind of separate them, but long story short, they're overall going to be an endothermic process, and so this isn't going to be favorable. There's just not conditions that are kind of suitable for this mechanism to achieve like a substantial amount of ideal product. And so HBr is exothermic, it's very favorable, and the process is great. We can get a high percentage of our desired compound. So if this is you right here in this mechanism or understanding this concept, then you need to practice. You know what I'm saying? We need practice, y'all. Because you're way off right now with that radical mechanism. I don't even know right now. Throwing stuff against the wall? What is that? This guy better be joking, by the way. Um, all right, so let me just throw down a couple structures, and I want you to, of course, pause the video and try them on your own, and then see if they match mine when we come back. Okay, so let's see. We got 1, 2, 3. Yeah, that'll be. Let me give you another one. Yeah, this guy's pretty chill. All right, so we got HBr and the peroxide of some sort, right? So this is going to imply a radical mechanism, not just your typical addition, okay? So this is not to be confused with Br2 and adding to the allylic position, okay? Remember, that's totally different. If you see HBr, you still want to think addition like across that double bond like you did with the ionic mechanism. But radical conditions give you antimacabre. Okay? Bada bing, bada boom. There's that guy. And there's that guy. We got this here. And then this one here. This one doesn't really matter though. All right, so I kind of want to give you another one just because these ones are all pretty chill, kind of lame. Not really lame, but they're not as complicated. So let's throw this guy at you. So we want to draw all the possible products, right? So let's go ahead and add, we have HBr and ROOR, peroxide. Now we want to add Br to this position here because it's less substituted, right? But it now is a chirocarbon, okay? So what we want to do is we give two stereoisomers, but then the wedge and the dash, okay? So, and this is going to be a racemic mixture, of course, because you can attack from the top or the bottom, right? Same story as before. All right, and that's it for HBr addition to an alkene, right? That's super chill. Uh, Good stuff, though. I like oh, I got to think now, right? So it's cool. I love that stuff. So polymers and polymerization are really just the same mechanism. Okay, so we're going to have a couple terms for you. Polymers are large molecules made up of repeating small units. Okay, and these small units are called monomers. Okay, it's like poly means many, mers, and then mono means one, mers. So if you probably already know that from like bio or something because proteins are uh, polymers of amino acids. But polymerization is the action of joining monomers or monomeric units together to make polymers. Okay. Oh, let me write this together to make polymers. Okay. All right, so let me do a little something for you just to kind of give you a generic example of a polymerization. So the most basic polymer or monomer that we would use for radical polymerization is ethylene. Okay, so it's the most basic pi bond we can have, right? And so if we have ethylene, there's the H's, and I'm also omitting those H's because that's annoying to draw. We can draw a polymer, which would be basically all of those guys jammed together, and the pi bond is gone. But those electrons from that pi bond actually helped create new sigma bonds to link all of those monomeric units together. Okay, so the blue I've drawn just to kind of show you where those original bonds in ethylene were, and then now the black ones are those are the ones that are linking them together. Okay, so those are the new bonds, I guess. All right, so that's kind of what a polymer is, right? It just takes up three monomers in this case and then jam them together and then get rid of the pi bond. That's it. Okay, so it's easy. But it can get a little more complicated, right? Of course. But HDPE and LDPE are high density polyethylene and low density polyethylene. I'm sure you've seen those, right? They're all over everything. And so I wanted to kind of introduce those to you and then explain what they are and how. I mean, you probably don't know the difference, right? So you're going to learn today. High density polyethylene, those are hard plastics, right? And then your low density polyethylene is going to be your soft plastics, like sandwich bags. Your high density polyethylene is going to be like bottle caps or something harder, like hard water bottles or something. All right, so let's introduce the idea, or let's talk about how to make polymers. Okay. There's definitely, you can do an ionic method or mechanism, but obviously we're going to talk about the radical mechanism here. And like I said before, the radical mechanism is similar to the HBr addition to an alkene, and obviously it's not going to have the HBr, and but I mean it. You have your peroxide initiator, and then uh, one radical attacks another radical, and then so on and so forth. And it's pretty. I think you could probably predict the mechanism if you really put some thought into it. Maybe you should even try that right now, just see how intuitive this is to you. All right, so we've got our RO dot, and that attacks the alkene. Okay, and so what that's going to do is put a radical at that terminal position, right? Or it could have been either side in this case, it would have been the same. And then that radical is now going to attack the alkene, right? So that's where the similarity comes when to the HBr addition to an alkene. And then that forms a new radical. Sorry, let me draw this guy a little bit differently. So it's like, yeah, looking good now. Cool. All right, so we got that radical there. It attacks another alkene, and you can see this can go on forever, right? So in theory, forever. There's obviously certain conditions that will promote really long chains and really short chains, or even branched chains, which you'll see what that is in just a minute. But once you form this is a polymer, and it's more like an oligomer, I guess, but you can see how it can get longer and longer, right? So let's say we took this guy and then we did that propagation step over and over and over again, and then along comes another one of those guys, and they're like, "What's up, dude? Let me hang out." And then they do hang out, and they become one, and they get married, they have kids, they get a dog, and I don't know, they buy a house, in no particular order, I guess. And then, okay, sorry, I'm too far, huh? Too far. All right, so we've got our. I was just struggling to draw this guy. I wanted to make sure how many carbons, make sure there was the right amount of carbons. So that was sorry, I'm joking. That was the polymer termination, right? And this termination actually could occur with an RO dot, and so it doesn't have to be another polymer. But I'm just showing you. The reason why I did that one was because I wanted to show you like how you can end up with a really long chain, right? But then, now that we've got this completed chain, what I really wanted to show you was the difference between a linear chain, which is this guy right here, and this linear chain is basically what we get when we have high density polyethylene, okay, and which is hard plastics, right? And the reason why they're harder plastics is because they have better or stronger intermolecular forces. That's because they're not branched. They have more symmetry. They can stack on one another, right? Stacks on stacks on stacks. And then, but chain branching, on the other hand, will result in your low density polyethylene. So what is that, right? So let's say we had that polymer and it formed right here. I went ahead and cut it off on both sides just for clarity, but we got a hydrogen here, right? And we hit it with the RO dot. Just remove a hydrogen is what we're doing, right? We can do that all day. That's kind of what we do in a radical game. So that dot can now attack a monomer, right? And so what we end up getting is we start adding not to the terminal position of that polymer, but to like somewhere in the middle of it. And then that starts to build and build and build. And I'm struggling. I got to move this guy somewhere. All right, so then that builds and builds. And so this is what we mean by branching. That is a branch. So then technically that could stop. And then the radical can swoop on a hydrogen somewhere else. And then you get really intense branching. And that branching is, the branched polymers in general, those are going to, if they're highly branched, they're typically low density polyethylene. Okay, and that weakens the intermolecular forces, and that's what gets you your softer plastics. Okay, bada bing, bada boom. What's up? Oh, was that not fun enough? Okay, cool. Because I got some more fun facts for you. All right, so sorry, I'm gonna try to draw this real quick. I'm not. I just want to do it fast. So, um, this is our little recycle, reduce, reuse, and close the loop, right? So, it has a number in it typically, and the lower the number, the better. Okay, so what I mean by better is the lower the number, the easier it is to recycle. Okay, so um, pay attention to those numbers, right? And you should be surprised how many are like 5 and 6. Six just popped up fairly recently. I feel like I always saw 5, but I didn't see sixes too often. But I do now, which is a bummer. Apparently, my children's playground is a 2, so I mean that's cool. I can recycle it, I guess. But it's a city playground, so I won't touch it. Um, All right, so the monomeric unit that we were using before was pretty basic, right? They can get more complicated, as I said, and that's basically when we have Z, some functional group, okay? And let me give you a variety of monomers just to expose you to them. We have propene here, where the Z is a methyl. Vinyl chloride, where Z is Cl. And then this is tetrafluoroethylene. That's, well, obviously the Z is the fluorine, but there's extra on there. Tetrafluoroethylene. Dang, I cannot write. I think it's my pencil. It doesn't like me right now. All right, so we've got some carbonyl compounds with alpha beta. They're alpha beta unsaturated carbonyls, and so those can be used as monomers as well. This is acrylic acid. And then we've also got styrene right here. There's a benzene ring with a double bond there, right? Okay. Okay, so let's take a look-see at kind of like a generic mechanism with Z on there, okay? We got our R dot swooping on an electron, and that puts the radical in a different position, right? So this is where it's similar to the addition to of HBr, right? You added the Br and the radical moved to the most stable position, and then you added the hydrogen. But instead of adding the hydrogen here, we're adding another carbon, okay, which is the monomer. We're building, and that radical addition forms another radical at the same spot, which is the most stable position. And you do it over and over and over again. That's the propagation, and then you build a polymer, right? And your Z, notice, kind of fancy, it's every other carbon, right? And that's the case. That's what you want to do if I ask you to draw me a polymer, basically with this functional group coming off of a double bond, right? And that's pretty nice, right? That's pretty simple, right? But that's in a wonderful world of basically you controlling it, but you might get a polymer drawn like this where it's all crazy and you got to figure out what the monomer is, right? So that's where it gets complicated because it's not always going to look pretty. So what I do is I highlight these guys in red because these are clearly all the same. So those are a portion of the monomer, right? But the question is, where's the CC double bond? Okay. Now I'm gonna try and draw these in blue actually, and so there's 1, 2, 3, 4, 5, 6 carbons, right? So obviously there's 3 monomers in here. We saw that from the carbonyl groups, but we need to figure out where they are. So that represents the Z. Okay, so that means that this pink line is the double bond. That's where the double bond is, right? Boom, 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 and there you go. So all you got to do is draw in that double bond where that pink is, and then that's your monomer, right? And this would be a what's it called? Polyvinyl acetate, okay? That would be the monomer. And so remember, the more substituted radical adds to the less substituted end, and that's kind of given the term head to tail. And so that can help you kind of identify maybe where your monomer unit is and what portion of it represents the monomer. Okay. So now what we want to do is kind of draw out what polymers would form from these monomers, right? So I'm just going to draw this. Boom. Remember, alternating Z's because it's every other carbon because we have an alkene and then a Z, right? And so that's our Z right there. And so what we can do is just remove that Z and actually in this case just leave the methyls there because it's propene, okay? And this is called polypropylene. Okay, and you're probably familiar with polypropylene. It's just plastics, right? So this guy right here, I'm actually just going to copy and paste this so that I don't have to keep drawing it. I don't know. I do things that are, I think are going to save me time, and they probably don't. It really doesn't matter if I copy and paste this, but Cl is my Z. So I basically just draw my Cl there. Boom. And that is, so the name is vinyl chloride, the monomer is, and so this is polyvinyl chloride for the polymer, aka PVC, like PVC pipes. All right, so F is fluorine is the Z in this case, but we got a lot of them on there. So basically every carbon has 2 fluorines on it. And so, yeah, I'm about to do that. I'm going to take this 5 minutes and draw on all the fluorines. You know what I mean? This one's cool. I like this. Tetrafluoroethylene makes polytetrafluoroethylene. Polytetrafluoroethylene is really cool. It's actually what your stir bars are made out of in lab. If you ever see them, they're like white. PTFE is the abbreviation. It's also known as Teflon. In case you didn't know, now you know. Acrylic acid, that Z is the carboxylic acid. So draw a bunch of carboxylic acids every other carbon, and that's a polymer of acrylic acid, right? Oh my gosh, easy peasy, guys. So easy. And then guess what the name is for this one? Here's one of those times where I'm going to try and save time, but it takes longer. Polyacrylic acid. Boom. That's what's up. That's what it is. And all right, so benzene ring here is abbreviated PH for phenyl. That's our Z. So that's what we got. And what do you think this is called? Polystyrene, of course, aka styrofoam. Boom. Now you know what styrofoam is, right? There you go. So here's the thing. We want to know what these things are made of or what they're for, right? So plastics, PVC pipes, Teflon. Teflon's super cool because it's like everywhere. I think dental floss. It could be tape for your gas lines, your pipes or whatever. It's on your pots and pans. I told you it's on your stir bar. So that guy's baller. Styrofoam for polystyrene. Oh, polyacrylic acid is diapers, and it's also like these for plants. LOL is what that's supposed to say. And it's actually the acrylate, polyacrylate, where you remove that proton on the acidic carboxylic acid and you make a carboxylate, so that's why it's polyacrylate. And those little beads absorb water, and that's why they're for plants too. Because you ever seen those colorful balls that you like soak in water and then you put them in your pots and whatever, and then your plants absorb the water? That's polyacrylate. So cool stuff, right? Polymers are legit. Okay, bye.